Hello everyone, I am Charvitha and today I'll be presenting a case study on yield curve prediction. So, introduction. Our main objective in this case study was to accurately predict bond yields across different maturities, focusing on the 1 month, 5 year, and 30-year yields. Yield curves, which plot interest rates of bonds with equal credit equality but varying maturities, play a pivotal role in financial markets. They help us understand future economic trends, interest rates, and inflation. By leveraging both historical yields and related macroeconomic variables like federal debt and corporate spreads, our goal was to enhance the model's predictive power. Moving to the problem definition, predicting the yield curve is quite challenging due to its dependency on a highly volatile economic environment. Various factors, including interest rates, policies, and economic conditions, constantly influence the yield curve. In this project, we needed to create a model that balances accuracy in both short and long term predictions, adapts to changing market conditions, and remains computationally efficient. These complexities made our approach to yield curve prediction both interesting and demanding. Yield curve prediction involves navigating multiple challenges. For example, market factors influencing yield change frequently, so our model needed flexibility. Additionally, ensuring real time processing and maintaining computational efficiency are crucial for timely insights. The model also needed to be monitored continuously so it adapts to economic shifts. To meet regulatory requirements, we carefully handle data privacy while focusing on designing a model that remains reliable under evolving conditions. Feature engineering was essential in capturing the economic patterns affecting yields. We utilized historical yield data and selected additional macroeconomic indicators such as federal debt and corporate spreads. By carefully engineering features and applying feature selection techniques, we could reduce noise and focus on impactful variables, balancing depth and efficiency in our final model. To accurately predict the yield curve, we evaluated multiple models from basic linear regression to more complex artificial neural networks or ANNs. Linear regression served as a solid baseline while ANN, with its adaptability to nonlinear relationships, captured market dynamics more effectively. We used mean square error MSE on an 80-20 train test split for evaluation, and grid search helped optimize ANN's performance by fine-tuning parameters to reduce error. Class imbalance was another critical challenge. When data is skewed, it can lead to biases, where the model favors majority classes over less frequent but significant cases. To address this, we tried random undersampling, ADASYN, cost sensitive learning, and smooth. Each method contributed to making our model more balanced and sensitive to variations in economic conditions, improving its predictive power. Once developed, the yield curve prediction model was deployed in a real time system. This allowed for continuous predictions of bond yields, providing valuable insights for investment and risk management. Monitoring the model is essential to ensure accuracy, especially in a dynamic market. By setting up alerts and retraining periodically, we aim to maintain reliability, helping investors make informed decisions based on the latest trends. So, coming to our code, we import key libraries needed for our analysis. Pandas and NumPys are foundational for data manipulation, allowing us to handle and preprocess data efficiently. For data visualization, we use matplotlib and cbond, which help us uncover trends and patterns in data through various plots. Finally, scikit-learn is essential here for accessing machine learning tools like model selection, scaling, and evaluation, enabling us to develop and assess our predictive models effectively. So next, we load the data using Pandas data reader, which fetches yield curve data and related economic indicators such as federal debt and corporate spreads. During data processing, I create new feature that captures the percentage of federal debt held by government and foreign entities relative to total debt. This feature engineering step is crucial because it helps to incorporate economic insights into our model, enhancing its understanding of how these factors impact bond yields. The next is exploratory data analysis. So, in the EDA analysis phase, we dive deeper into the data to visualize yield curves behavior over time. We plot uh, diff- different types of tenors, which lets us observe how short term and long term yields interact. Additionally, a scatter plot matrix highlights correlations between key variables, helping us understand the interdependencies that may influence bond yields. EDA is a vital step as it guides our feature selection, which is essential for building a robust model. So, the next is data preparation. With EDA complete, we move on to preparing data for model training. I define the target variables as the yields for 1 month, 5 year, and 30-year bonds. The feature include various tenors along the engineered economic indicators. Standardization of the features ensures they're on the same scale. A crucial step, especially when using models like neural networks that are sensitive to scale differences. The next step is model training. So, in this step, I train 6 models: linear regression, lasso regression, elastic net regression, k nearest neighbors, CART, and artificial neural network MLP. Each model is trained to predict bond yields, and I use mean squared error MSE as the metric to evaluate both the training and test sets. This approach allows us to measure each model's accuracy, making it easier to compare their performance in predicting yield movements. So, after the evaluation, we compare the models and algorithms. So, we visualize the algorithm performance. So, we create a bar chart to see the algorithm comparison of all the models. So next we move on to the model tuning and grid search. To further enhance the ANN's model, I use grid search to tune its architecture, experimenting with different configurations of hidden layers. By optimizing parameters like the number of layers, we can better capture complex market dynamics that affects bond yields. This tuning reduces prediction error and helps the ANN perform at a level closer to traditional linear models. Next, prediction and comparison of the visualization. So finally, I use the trained ANN and linear regression models to generate predictions and create a comparative plot. This visualization illustrates how closely each model's prediction uh, aligns with actual yields for the 3 tenors. Through this comparison, we can identify where each model performs well and where it might need improvement, providing insight into their effectiveness for their yield prediction. Thank you.